talked about the intersection of the set of points with bounded trajectories. I should also have mentioned the work of Aravinda, who is one of the organizers of this conference. Aravinda's thesis concerns this problem where he considered points on C1 curves with this property. And subsequently has also worked with Leisinger and also Roushon and Sankaran. Thank you.
Okay, so our second speaker has made life easy for me. Our speaker is Emmanuel Breuillard, who's speaking from Marseille, who's talking on approximate groups.
Okay, well, thank you. So, first of all, I would like to thank the organizers for this invitation. I'm very happy to be able to speak here in India. So, as the title suggests, I'm going to talk about approximate groups. So, I guess many of you probably haven't heard of approximate groups because it's a new term, a relatively new subject. So, I'm going to, this talk will be more or less like a survey talk about approximate groups. And I will try to describe the recent, the definition first and then the recent results regarding them. So here's the plan of the talk. So first I plan to discuss what's called the non-commutative Fryman problem. So this is also can be called the classification of approximate groups. So this is the main problem I'm going to be talking about today. I will define it in a second. So then I will discuss recent theorems of Roushon. So Roushon is a logician, and he came up recently with a method to classify approximate groups. And in the process of doing so, he managed to generalize the famous Gromov theorem about polynomial growth of the polynomial growth theorem of Gromov. So I will explain this also. And in a third part, I will describe the recent effective versions of these theorems of Roushon, in particular for linear groups. And that's a joint work with Ben Green and Terence Tao. And in the fourth part, I will describe some applications of these theorems to the expander graphs, to so-called expander graphs. So I will also define this later. Okay, so okay. So somehow you cannot see the title over there of this slide, but okay, maybe it doesn't matter. So this is I'm going to talk about the non-commutative Fryman problem. So here's the problem. Okay, so let K be a number, a parameter. Okay, let G be a group. Okay, and A is a finite subset. So by A between two bars, I will denote the number of elements in A. Okay. So here's the question. So what can you? So it's a really vague question at the beginning. So what can you say about A if all you know about A is the fact that the size of A times A is at most K times the size of A. So A times A is the set of products of elements from two products of elements from A. A times A is A1, A2. Okay. Both of them belonging to A. Okay. Sorry? Maybe I should turn off. Okay, how do you turn off the light? Here. Yeah, the top of the board doesn't, but that I don't know what to do about it. Okay, hopefully there won't be anything really important written on the very top of the board. Okay. Okay. So, is that better? No. Okay. Okay, so So it's the first time I do a Beamer presentation, so please be considerate. So, okay. So you understood the problem. Okay, what can we say about set A if we assume that the number of elements in A times A is at most k times the number of elements in A? So of course, this number of elements in A times A is at least the number of elements in A, and at most the number of pairs, so at most A squared. Okay, so it's in between. And we have a fixed parameter k, and we ask, what can we say about A if this number of elements is at most k times the size of A? Okay, maybe 10 times the size of A, maybe 100. Okay? So this problem was first considered in the case when G is an abelian group in the context of additive number theory and combinatorics. So there are many famous names in combinatorics like Fryman, Roushon, Erdős, Szemerédi, who were interested in this problem typically when the group is Z or is an abelian group. Okay? Then renewed interest took place in recent years with the Green-Tau theorem in arithmetic progressions on primes and the Bourgain-Gambrod new construction of expander graphs. So in particular for the finite groups SL2 Z mod PZ, they were able to construct new generating sets of these scatter graphs which make them into expanders. And it has also applications to some parts of number theory, in particular the recent work of Bourgain, Gambrod, and Sarnak on the affine sieve. Okay, so these works were using the answer, or the answer that I'm going to talk about the answer to this problem. Okay, and what happened last summer, Roushon released a remarkable paper in which he studied this problem using tools from model theory and logic, and he managed to give some answers that are valid in every group. And in particular, he obtained, in fact, quite recently, a generalization of Gromov's theorem. So I'm going to state this in a second. So here are some examples or exercises so that you can get a feel of this problem. Okay, so maybe the first thing to look at is what happens if the size of A times A is equal to the size of A. Okay, what happens? Then, of course, this is if and only if A is just a coset of a finite subgroup. In fact, a normalizing coset of a finite subgroup. Okay? That's a very easy exercise that uses just the basic axioms of group theory, right? Just an undergraduate exercise. Here's a slightly more tricky exercise. Suppose that A times A is less than 3/2 the size of A. Then what can you say? Okay. Well, then it's quite remarkable that you can say something actually. So you can say that A is contained in a normalizing coset of a finite subgroup. Okay? And a finite subgroup that is not much bigger than the size of A. So if A times A is less than 3 times the size of A, then A is contained in a normalizing coset of H, where H is a finite subgroup of size at most 3/2 of A. Okay? And of course, that's if and only if, because this direction is very simple, right? If you have any subset containing A times H satisfying this, then of course A times A is at most 3/2 A. Okay? So that's also an exercise slightly more tricky, as I said. Here's another example, maybe that's the easiest and most important example. What happens when G is Z, the cyclic group, and you take A an interval, 0 up to n. Then A plus A is the 0 up to 2n. Okay, so in particular, A plus A is at most twice the size of A. So this example already tells you that number 2 here, the number 2 here is the 3/2 that you can see here is sharp. Okay? Because if you take n equals 1 here in this example, then you get a set such that A plus A is exactly 3/2 of A. Okay? But yet there is no normalizing coset, no normalizing subgroup. There's no subgroup, no finite subgroup in Z except 0. Okay. So yes. So and here's another example, which is somewhat a generalization of this first one. As you take just any ball in the Cayley graph of a nilpotent group, okay, and if you fix the nilpotent group, then if you take a ball of radius n, then A times A, if A is this ball of radius n, then A times A will be at most K times A, where K depends only on the group, on the nilpotent group, and the set of generators. Okay? So this is the typical example of a group of polynomial growth. If you take the ball of radius n, then the ball of radius 2n, which is A times A here, will be not much bigger than this ball of radius n, in fact, only a factor bigger. Okay, so these are, you see, being a finite group, so that the first example, and being a ball of radius n in a nilpotent group, these are the two chief examples of sets A that satisfy this, that satisfy A times A less than K times A. Okay, so sometimes people call these sets of small doubling, or doubling at most K, because A times A is less than K times A. Okay, so these are the two main examples, and I will try to explain later why we believe that maybe, in a sense, they are the only examples. So maybe the first thing to try to understand is what happens when G is Z. Okay, so of course, as I mentioned before, this in the case G is Z, this problem has been studied very much in the past. And this is Fryman's theorem from the 60s. And it says the following. As soon as you have a set of small doubling, or doubling at most k, among the integers, then A is contained in a set called a generalized arithmetic progression. So it's a kind of structured set. What is it exactly? So what is a generalized arithmetic progression of rank D? So it comes with a rank. So it's basically a set which is a projection pi of B, where pi is an affine map, so a homomorphism composed with the translation from ZD to Z. And B here is just a box. So the product of intervals 0 to Li. So the Li's are the side lengths, so it may be a very skewed box, but just a box, and it's in dimension D. Okay, so it's clear that any such box set is a set of small doubling. In fact, of doubling at most 2 to the D. Okay? Any such box in ZD. And if you project by a homomorphism, then you're again going to this property of being of doubling at most k is going to be preserved. So in particular, every such set has doubling at most 2 to the D, okay, where D is the rank. And Fryman's theorem is a converse to this. It says that any set of small doubling is essentially, so what does it mean essentially? It means it's contained efficiently in an arithmetic progression. So it's contained in an arithmetic progression P, whose rank is bounded in terms of K only, O of K to the C. Okay, so the rank is bounded by constant of K, and the size of P is only maybe slightly bigger than the size of A. So by a factor here which depends only on K only, also. Okay? So here we have explicit constants, here polynomial in K and here exponential. And these constants are, in fact, for applications, very important. So for example, here it's an important conjecture in combinatorics that this constant here should be brought down to a polynomial constant of K. Okay. Okay, so this is Fryman's theorem. So a simpler proof of Fryman's theorem was found by Roushon later on, and then generalized by Green and Roushon to an arbitrary abelian group. And those proofs typically they rely on harmonic analysis. And the idea is to identify inside A or inside A plus A what's called a Bohr set. So that a Bohr set is the inverse image of a character. To a torus. So I won't discuss this here, but this is just to let you know that this exists. And so, yeah, a couple of years ago with Ben Green, we extended Fryman's theorem to nilpotent groups. So as expected, essentially the same thing happened in a nilpotent group. So if you take, in fact, a torsion-free S-step nilpotent group, and if you take a finite subset with A times A is less than K times A, then this implies that A is in fact contained in an S-step nil progression of bounded rank and of size at most a constant times the size of A. So I have to tell you what is a nil progression. Okay? So nil progression, I won't exactly define it precisely, but let me just say that it's the natural analog of a generalized arithmetic progression. So instead of taking the image by an affine map of a box in ZD, you take the free nilpotent group that we heard of in the last talk. You take the free nilpotent group of rank D, so with D generators, and of nilpotency class S. And inside it, you take a nil box. So a nil box is the analog of just a box. Okay, so it has side lengths, one side length for each generator. And this basically gives you a box which in a sense is the same thing as the ball of radius n for a certain generating set, and or like a Carnot-Caratteau-Dori ball for those who know what they are in the nilpotent group. Okay, so you take this nil box and then you project it by a homomorphism to the nilpotent group you are interested in. Okay, and maybe you translate it by group translation. Okay, so right, so this is what we call nil progression, and this is the theorem, which is just the analog of Fryman's theorem. So I forgot to mention that Katz, Fisher, and Ping have obtained a similar result roughly at the same time. Okay, so this brings me to the definition of an approximate group. So this definition was introduced a few years ago by Terence Tao, precisely in order to have a tool to answer this problem of the noncommutative Fryman problem, classifying sets A for which A times A is less than K times A. Okay? So here's the definition. So G is a group, okay, and K is a parameter, and a finite subset A of G is said to be a K approximate group if you assume that A is stable under inverse. Okay, so A is a finite set. Every element in A, its inverse is also in A. It contains the identity of the group. And the key property is that A times A is contained into at most K cosets of A itself. So A times A is contained in X times A, where X is a subset of G of size at most K. Okay. So here I put X on the left, but you could put it on the right if you want, just by if you take inverses, because A is stable under inverse, you get A times A is contained A times X inverse as well. Okay. So this is the definition. So in particular, if you take K equals 1 in this definition, then you recover the definition of a subgroup, okay? Because a subgroup is nothing else than a finite subset that is stable under multiplication. Okay? So if K equals 1, then A times A will be contained in A, and you have a subgroup. So in a sense, K approximate groups. So maybe I should say K approximate subgroups of a given group G. They are approximations, so they are well named. So they are approximations of a finite subgroup. Okay? So there are subsets that, in some sense, look like subgroups. No. So it's possible to demand that X be contained in A times A times A 3 times. Okay, because A times A will be x times A. So x can be, you can assume that x belongs to A times A times A. But no, you don't assume that it's contained in A. Right? Yes. Okay, so yeah, so that's a key point. You ask A to be finite, but you're right that this definition makes sense without this condition. Okay, so you can also talk about infinite approximate groups, but I won't be talking so much about them. Although we'll see that in particular in Hrushevsky's theorem, they appear with A infinite. So okay, so approximate groups enjoy many nice properties that are often approximate counterparts of the basic group theoretic properties. So in particular, if you try to think about approximate groups, it's nice to first try to think about subgroups and then try to see if your argument, which used group theoretic arguments, okay, may be able to, if you may be able to extend it to approximate groups. Okay, so it turns out that many arguments from pure group theory have an approximate group analog. Okay? Not all of them, but certainly quite a bit of them. So in particular, here are some of the, we call it the basic yoga of approximate groups. So if you take a subgroup H of G, then if you intersect an approximate group, or in fact it's squared, here A squared, A times A, by a subgroup, then you again get an approximate group, but maybe by a different, another constant, okay? Instead of a K approximate subgroup, you're going to get a K cubic approximate subgroup. Okay, so if you just intersect by a subgroup, you again get an approximate group. Or if you take quotients, then it's completely obvious. The property for subgroups is not entirely obvious, but for quotients, it just follows readily from the definition that if you take an approximate group and you take a quotient of it, then you again get an approximate group with the same K. Okay. Right. So these are just two examples of the good properties that approximate groups have. So what's the relation between approximate groups? Why did I introduce this definition? The reason is because there is basically they are really, approximate groups are a tool to answer or to try to tackle the noncommutative Fryman problem. So here is the relation between having small doubling and being an approximate group. So here, instead of small doubling, I will assume this slightly stronger condition, that A times A times A is less than K times A. So this is called small tripling. I have three copies of A. So there's a slight difference between the two. So I'll explain it in a second. So suppose you have this slightly stronger condition. Then it's a really remarkable thing that, in fact, as soon as you know it for 3, so here A is any set in any group, okay, any finite set. As soon as you know this for 3, you know this for n, for every integer n. Okay? So A to the n is the nth fold product set, A times A times A n times. So it's enough to know that A times A is less than K times A to deduce that you have a similar bound for the nth fold product when n is bigger than 3. Okay? And you get here a slightly worse constant, K to the n minus 2n minus 2, but you do get a constant which depends only on K. And moreover, it's enough to take so of course if you want to make out of A, if you want to make an approximate group, you need to take inverses and you need to add the identity. Okay, so let's take the inverses of A and let's add the identity. And out of this I take the square, so I take the product set with itself. Well, it turns out that this is an approximate group. In fact, a C, K to the C approximate group, where C is an absolute constant. Okay. So this is for small tripling. Here, for small doubling, you have a slightly weaker statement. Namely, if you assume a small doubling, A times A is less than K times A, then A will contain, what happened is that maybe A will not be an approximate group, or you won't be able to make an approximate group out of A, but a large subset of A will lead to an approximate group. So if you take any large, so not any, but there exists, the theorem says that there exists A naught a large subset of A, a large chunk of A, such that if you take the 3, this time A node has small tripling, okay, with a constant here which is only slightly worse than K. And again, now that you have small tripling, you can apply part 1 to get an approximate group. So this proposition is just to let you know, convince you that in order to solve or to tackle the noncommutative Fryman problem, so to understand all finite sets A of small doubling, it's enough to assume that A is an approximate group. Okay? So when I say enough, well, it's modulo these two propositions. Okay? So from now on, I will mostly look at sets of small tripling, because small doubling is slightly annoying. You have to go to this to a subset of positive density here, while if you assume small tripling, as this proposition shows, you immediately get an approximate group, and this is preserved under taking powers a to the n. Okay, so the difference between the two comes from if you take a set A of this form, X union H, where H is a subgroup, and you assume that H is that X conjugates H outside of itself. Okay? Then suppose H is a large finite subgroup. Then A times A, suppose you have this, then A times A is nothing else than H union the cosets HX union X squared. Okay? So this is A times A. So we see that A times A is no more than 3 times the size of A. However, A times A times A contains this guy, and this guy has cardinality H squared because of this assumption. Okay, so this gives you an example. So this is 3 times. Okay, so this is an example of a set of small doubling such that it won't have small tripling. Okay, right. So this is why we talk about small tripling in non-commutative groups. So in the case when you have a commutative group, then small doubling is enough. Okay, let me just move on. Okay, so what comes in the proof of this proposition? Well, this is basically combinatorics. So two key ingredients are the Breuillard distance. So this is a quite remarkable distance, actually, that you can put on finite subset of a group. So you have a group, you have finite subsets of a group, and you form this quantity, the log of the size of A B inverse divided by the square root of the size of A squared size of B. Okay, so this is non-negative, easy exercise. Okay, and it satisfies. Okay, it's not moving anymore. Sorry. It satisfies the triangle inequality. Okay. So, in particular, you have like a pseudometric. So it's not true that the distance between A and A is 0 necessarily. Or it's not true that if the distance between A and B is 0, then A equals B. That's not true. However, you can characterize sets A and B for which the distance between the two is 0. Okay. But that's quite a remarkable fact, actually. So this is this is a key tool to go from small tripling to small n-pling. Okay. And so the proof of this triangle inequality is really just a couple lines. It's really not hard. Item 2, so in the proposition, on the other hand, is much harder. So it relies on the so-called Balog-Semiradi-Gauss theorem, or lemma. Okay. So this was just to tell you basically the basic propositions of approximate groups and what they are. And here is what we believe is probably the most optimistic answer to the non-commutative Fryman problem. So again, I remind you, we're trying to classify sets such that A times A times A is less than K times A. And we already have we have candidates for this. We know that A could be a finite group, that's obvious. Or we know that A could be like a nil box, or the projection of a nil box, so nil progression, like something like the ball of radius n in the Cayley graph of a nilpotent group. We know that these two are examples to be considered. So, well, maybe a naive guess would be to state this conjecture. So we call it the Helfgott-Lindenstrauss conjecture because we heard both Helfgott and Lindenstrauss give a conjectural statement of this kind. So basically one would like to say the following. So suppose K is a parameter, then there will be numbers K1 and K2 depending only on K, such that in any group, and for any K approximate subgroup A, A will be contained in at most K1 cosets of an HL set of size HL bounded by K2 times A, and nilpotency class and rank at most K2. So what is an HL set? Well, it's what you expect. So H will be a subgroup, and L will be a nil progression. So an HL set is a set of the form H times L, where H is a finite subgroup, and L is a finite subset. So H is a finite subgroup of the ambiguous group G, and L is a finite subset, which normalizes H, okay, and such that the quotient HL mod H generates a nilpotent group, and in fact is a nil progression in that nilpotent group. And you also need to ask for bounds on the nilpotency class and on the number of generators of that nilpotent group. Okay. So this is what. So far we don't have a counterexample to this statement. Okay. So a year ago, Udi Hrushevsky released a really remarkable paper, and using model theoretic tools, he tackled the above conjecture, and in fact, the noncommutative Fryman problem. And he managed to give answers that are valid in any group, but answers towards this conjecture, or at least, let's say, something which would be trivially implied by the conjecture, but which are already non-trivial. So let me now describe some of his results and methods. So let's, again, K be a parameter, and let Gn be a sequence of groups. Okay, so you have just a sequence of groups. And An is a sequence of finite subsets of these groups. Okay? And you assume that there are all K approximate subgroups of Gn with the fixed K. Okay? So for instance, you could have all the Gn's are the same group of polynomial growth, and the An's are balls of radius n for increasing radius. Then the polynomial growth tells you immediately that they are approximate groups, okay, with the fixed K. K would be 2 to the C, where C is the degree of polynomial growth. Okay, that's just one example. So let's stick to this generality here. So what one can do is to try to form the ultra product G hat. So you take a non-trivial, non-principal ultra filter, U, and you take the ultra product G hats of the group Gn's. And you call A hat the ultra products of the ANs. Okay, so you get a new group, G hat, and you get a new set, A hat. Okay, this time A hat is typically infinite, because the cardinality of the ANs are going to infinity. Okay, well, I'm not requiring this, but this is typically, if the cardinality of the ANs are fixed, then there's not much to say. So G hat is a group, and A hat is still an approximate group. That's the point. Okay. But as Enrico mentioned, here it's a K approximate group, but it's not a finite one, maybe infinite. But otherwise it satisfies the same axioms. Okay. So using model theory, Hrushevsky was able to construct a certain subgroup of H of this ultra product G hat with the following property. H is a subgroup and it's contained in the fourth power of my new approximate group, A hat. H is a normal subgroup, so it's normalized by A hat. So you see we're already starting to get towards this Helmholtz-Lindenstrauss conjecture when we had this set A, this HL set. So this H here will correspond to the H from the Helmholtz-Lindenstrauss conjecture, or will be close to it. So, and the group generated by A hat divided by H is endowed with a natural topology, so Hrushevsky called it the logic topology. And this topology is locally compact. So it already tries to look like very much, for those of you that are familiar with the proof of Gromov's proof of the polynomial growth theorem, it starts looking very similar to it. And indeed, in fact, this idea of taking ultrafilters, in fact, was introduced later by some logicians, but this is really at the heart of the proof of Gromov's. So the local compactness here comes from the fact that you have an approximate group. So this fact that A times A is contained in K times A, it means that A times A can be covered by at most finitely many, at most K cosets of A. And the fact that K here is fixed all over has the consequence that this topology, although I'm not telling you what H is precisely, but it has the consequence that this quotient here is locally compact. Okay, so now that we did basically nothing here except that we have this nice setting, and we started with a very general sequence of groups and sequence of approximate groups. But now that we have a locally compact group here, we can apply the structure theory of locally compact groups, just like Gromov did in his proof. Okay, so the Gleason-Montgomery-Zippin structure theory of locally compact groups. And in particular, this structure theory will tell you that there will be an open subgroup of that quotient, which will be a generalized Lie group. This means that it will map, so in every neighborhood of the identity, you're going to be able to find a normal closed subgroup, such that if you quotient by it, you're going to get a Lie group. Okay, so using this, Hrushevsky managed to show the following non-trivial facts about an arbitrary approximate subgroup of an arbitrary group. So if A is an approximate group, K approximate group, then there is a constant K1 depending only on K, and there is a large subset A1, X1 of A to the 4. So large means X1 is bigger than the size of A divided by K2, so it's a positive proportion of A, with the property that it is stable under commutators. So, yeah, and in fact, Hrushevsky managed to show that you can not only find a subset stable under commutators, but you can find an arbitrarily long sequence of nested sets, each of them being of a positive proportion of the one before, and such that the product set of one of them is contained into the one before, and the commutator, it gets smaller every time. So where does this come from? Well, morally speaking, it's quite clear, given this fact that we have a locally compact group, and we can apply the structure theory of locally compact groups, because we get this Lie group, we get this quotient Lie group, and what are the xi's going to be? Well, they're going to be the pullbacks of a small sequence of neighborhoods of the identity in your Lie group. So if you take a Lie group, a connected Lie group, and if you take a small ball around the identity, and a nested sequence of small balls, then they will satisfy those properties. Okay. Xi squared will be contained to the next one, and the commutator of two small balls will be much smaller, will be contained in a much smaller ball. Okay. So these sets are the pullbacks of neighbors of the identity in the corresponding Lie group. Okay. 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 So using this machinery, Hrushevsky was able to apply this to a special case of when you look at a linear group. So Gn is G of K of n. Is an algebraic group of a field, and he basically gave a complete answer to this conjecture. So he solved this conjecture in the case of linear groups, in the case, in fact, of simple algebraic groups. So, in fact, he gets a much stronger result, which says that if you take an arbitrary, almost simple algebraic group of dimension as most d over an arbitrary field, then, and if you take there is one line missing here. So if A is an arbitrary subset, okay, so if A is an arbitrary subset of G of K, then either A times A is bigger than the size of the group generated by A, or A times something, a function that grows with the size of A. So either, you see what this means here, this part here, says that either A times A is much bigger than A, so you don't have an approximate group, okay, you don't have small tripling, or you are already the group generated by A. Okay? So if A times A is equal to the group to the size of the group generated by A, then of course it's at most. So if A times A is bigger than the size of the group generated by A, then A times A is the group generated by A. Okay, so if you have any finite subset of a simple algebraic group over an arbitrary field, either it expands under taking three products, or if you get three products, you already get it, or it generates a finite group, and this finite group is A times A times A. Okay. Okay. So that's this part of the alternative, and what happens? If not, well, if not, then it means that the size of the set A, so I forgot A is contained here, either A is contained in a proper algebraic subgroup with boundedly many connected components. So either A is degenerate, it's contained into a proper algebraic subgroup, or it either generates the group, or it generates a finite group, and in 3 times it's equal to this finite group it generates, or it grows. And this f here is a function which goes to infinity with the size of A, but the proof by logic using this outline that I explained before is just is not giving you any bound on f. So right. So this was for simple algebraic groups, but basically using this you can extend. And this is what Hrushevsky did in his paper also. They extend this to a complete proof of the HL conjecture for approximate subgroups of GLDC. Okay, so not assuming anything on the algebraic closure or being in a simple algebraic groups or anything like this. Okay, so we know the HL conjecture for linear groups, at least in characteristic 0. And the third theorem that Hrushevsky proved in this direction, using similar methods, is the following generalization of Gromov's theorem. So this time you take gamma a finitely generated group, okay, and you take AN to be an increasing sequence of finite sets, exhausting the group, and you assume they have small doubling. AN squared is less than K times AN. Okay, then the conclusion is that gamma is virtually nilpotent. Okay. So it clearly extends Gromov's theorem, because if you take AN to be the ball of radius n in a group of polynomial growth, then it will satisfy those hypotheses. Okay. So the point here is that Hrushevsky's proof is not using any metric. In fact, it's just there's no asymptotic cone. There's no well, there's this ultra product, okay, but basically no metric, and there's no assumption at all on AN except that it has this property. Okay, so now I'll move on to my work with Green and Tau. So what we tried to do when we saw this paper of Hrushevsky is to improve the bound on the function f. And for this we were motivated by various results and various conjectures by Breuillard and Gambrod on expander graphs. So we managed to get an effective proof of the second theorem of Hrushevsky, actually a different proof. We're not using ultrafilters, we're not using this logic topology, or this we're not using Montgomery-Zippin, but we got the same theorem, except that here instead of the function f, we have that the function f is a power of epsilon. So x to the epsilon, where epsilon depends only on the dimension of the algebraic group and nothing else. Okay, so if you take in a simple algebraic group of fixed dimension of an algebraic closed field, so these things don't depend on the field. Okay, and you take a finite subset, then either it's degenerate, it's contained into a proper algebraic subgroup, or it has this nice property that the triple product expands by a factor a to the 1 plus epsilon, or is already the group, or already generates a finite group, and it's equal to the group it generates. Okay, so, and additionally, we also obtain a complete proof of the HL conjecture for GLDC with these effective polynomial bounds. Okay, so, yeah, so this theorem was proven, in fact, at the same time, independently by Pieber and Sabo. So they were mainly concerned with the case when K is the algebraic closure of a finite field, because, in fact, that's the hardest case, because you have, for example, in GLD of FP bar, you have many subgroups, many finite subgroups. And you have to struggle then with all those finite subgroups, and that's actually the hardest case to consider. So before this, this theorem I had stated was in fact discovered and proved by Helfgott in the case of SL2FP, and then generalized also by Helfgott to SL3FP, and by Helfgott and Gill to SLNFP, where FP P is prime and N is, so they managed to do SLNFP for sets A of small size compared to P, not for all sets A. And so their methods was combinatorial, used the so-called sum product method in combinatorics, while our method is more, so I'll talk about it in a second. So, and also in a recent joint work with Ben Green, so we managed to give a geometric proof of this theorem I just mentioned in the case of compact Lie groups, and a completely different proof using a Bezikovich type covering argument. So, yeah, maybe I'll skip this. So, okay, basically I'll go fast on this. So the idea of the proof of the theorem I stated, this generalization of Hrushevsky's theorem, this improvement of Hrushevsky's theorem that we proved with Green and Tau. So what we use is a very nice preprint of Larson and Pink from 15 years ago, where they classified the subgroups of algebraic groups. And basically, reading this paper, we understood that in order to classify approximate subgroups, you first have to classify subgroups, and then try to see if your arguments for subgroups extend to approximate groups. And indeed, they do in many instances, and this was an important step forward when we realized that. So one of the things we have to use is this Larson-Pink estimate that they prove in order to classify all finite subgroups of GLN of our field. That if you take a finite subgroup and you intersect it with a subvariety, then the number of points that you find on that subvariety is small. How small? Well, smaller than the size of the subgroup, or the approximate subgroup, to the power of the dimension of V divided by the dimension of G. Okay? So they proved this when A is a subgroup. And we realized that their argument actually works when A is an approximate subgroup. Okay. Okay. Then the second step is the second step you get the contradiction by acting on the variety of tori of your algebraic group, and by counting tori. So I won't explain that too much, but subscript. This one. So this is analytic number theory. This is the Vinogradov notation. This double script means it's a big O, and the subscript means the constant in the implied constant in the big O depends on V here. Okay, so V is a variety. In fact, it depends only on the complexity of V. So only on the degrees of the number of irreducible components of V. And we have to apply this inequality to the case when V is a torus and the case when V is a conjugacy class of an element. Okay, so I'll skip this because it would be hard for me to explain this in details in two minutes. So maybe also skip this. So there are other instances where the HL conjecture is known for free groups. In fact, for hyperbolic groups, we also have a proof now that if you take an approximate subgroup of a hyperbolic group, then in fact it's contained into boundedly many cosets of a cyclic group. So in fact, either if you have a hyperbolic group and you take a K approximate subgroup, either you contain in a cyclic subgroup or you are bounded by a function depending on K only. And we have actually an argument that works for every uniformly non-amenable group. But the bounds are quite bad, so it's likely that very good bounds like this. So that's actually this is a quite remarkable recent result of Safin. That if you take the free group, so it's well known that free groups have exponential growth. But if you take the free group, then Safin gets a lower bound on the rate of growth of a free group, of the Cayley graph of the free group. A lower bound depending on the size of the generating set. Okay? So actually you have this bound for any generating set A. Okay. Also, quotients of Burnside groups by Roushon. So let me now move on to in the last minute to expander graphs. So in fact, most of the motivation for the study of approximate groups for us came from work of Bourgain and Gambold on expander graphs. So I remind you that infinite sequence of graphs, of finite graphs, is called an expander sequence, an expanding sequence, or a sequence of expanders, if the first eigenvalue, the first non-zero eigenvalue of the combinatorial Laplacian on these graphs is bounded away from zero by a constant. Okay. So it's called an epsilon expander if this lambda 1, the first eigenvalue, is bigger than epsilon for all members of this sequence of graphs. Okay, and there has been a lot of interest in recent years, also motivated by computer science, to build expanders. So the first expanders were built explicitly by Margulis in the 70s using relative property T. But recently, Bourgain and Gambold gave a machine, not just a new result, but they basically gave a new method to show that certain finite groups are expanders. And they proved the following, that if you take, so this is their result, if you take a Zariski-dense subgroup of SL2Z and you reduce mod P, then you will get a family of finite graphs, so the Cayley graphs of SL2Z mod PZ, and they show it's an expanding family. And the method is based on random walk arguments. And at a key point in the method, you have to use the classification of approximate subgroups of SL2 Z mod P, Z when P is very large. And this classification was in fact discovered and proved by Helfgott in 2005, shortly before Bourgain and Gamble proved their results. So now that we have this extension of Helfgott's result or this improvement of Roushon's theorem, this Breuillard-Green-Tao theorem I mentioned earlier, we can generalize this Bourgain-Gamble theorem. Basically, the method just extends, and now this Bourgain-Gamble theorem holds for every Chevalier group over Z. I should mention that Varjou and Salehi-Gorsafidi, in fact, managed to generalize this greatly to perfect groups, and also not only to taking square mod P, but they look at mod Q, where Q is not a prime. So, so in maybe the last remaining 2 slides, I will talk about this random expansion thing. So, a few years ago, Kasabov, Lubotsky, and Nikolov, they showed that if you take the family of all finite simple groups, then you can find K-graphs, you can find generating sets in them, such that altogether they form a family of expanders. Okay. And except that they couldn't do the Suzuki groups. Okay, so the Suzuki groups are a certain family of finite simple groups. So it turned out that with this method, this Bourgain-Gamble machine, together with our theorem, we can also treat the Suzuki groups. So now we know that the family of all finite simple groups can be turned into expanders. So this means you can find generating sets such that the corresponding Kelly graphs are expander graphs. And in fact, we show that if you take the Suzuki group, so the Suzuki group is a certain family depending on the finite field Q, FQ. So Q tends to infinity. And in fact, we show that if you take a random pair of generators, or in fact a random pair of elements, then they will generate, and the corresponding Kelly graph will be an expander graph. Okay. And finally, recently, together with Bob Guralnik, we managed to extend this to the high rank situation, because the Suzuki group are in a sense rank 1, and we managed to extend this to all high rank finite simple groups. So you take G as an arbitrary simple algebraic group defined over a finite field FQ. You look at G of FQ, so typically this will be not necessarily really a simple finite group, but quasi-simple. There would be maybe a center, or you have to go to a finite index to get a really simple group. But never mind. So if you take G of Q, if you take 2 elements, you choose at random in G of Q, then they will generate the group, and the Kelly graph will be an expander where the constant in the expanding thing depends only on the rank or the dimension of the algebraic group. Okay. So again, the proof follows this Bourgain-Gamble strategy and uses our theorem. And at some point, it has to use also. So the Bourgain-Gamble strategy basically it tells you that in order to prove that something is an expander, what you have to do is to run a random walk, a simple random walk on the Kelly graph. And proving that this is an expander graph is essentially equivalent to prove that the random walk decays very fast. In fact, equidistribute very fast. And a preliminary step is to show that the probability of return to the identity of that random walk decays fast. Okay? So fast means that in log of the size of the group steps, after a time you wait log G, then you will get the probability of return will be at most 1 over size of G to a parallel